Pathfinder mathematics, right? What's in the course for us? Polynomials, inequalities, induction. Yeah, I think I can skip third one, whatever. Recurrence relations might be important. Function. Oh yeah, of course. Fifth, I'm going to do that for sure. Number theory. Not that important for what I'm trying to do, but yeah, we can do that. I already have a good background in number theory, so I think we can do that. Combinatorics. Sure, I guess we should. Geometry, maybe we can try that. Right. So let's start. And what is this thing? Answer key is appendix. Okay, whatever. So in polynomials, we have, okay, polynomial functions, division. In polynomials, remainder theorem and factor theorem, fundamental theorem of algebra, polynomial equations, metas, right? All these stuff that's usually introduced. No big deal. And what's this last thing? Irreducibility of polynomials. That's new. I don't know what that is. Well, we'll see. Mathematical induction, whatever. Right. Hey, what's in number theory? I want to see that. Divisibility of integers, Euclid's division lemma, greatest common divisor, primes, fundamental theorem of arithmetic, modular arithmetic. Well, I guess this is going to be a big section. So, yeah, so 21 to 27. That is a big section. Number of positive divisors of a composite number. I mean, that's actually just a formula. What's the big deal about it? Complete residue theorem. Okay, interesting. Some important function or theorem. And okay, scales of notation, Grayson function, pentine equations. So yeah, a lot of this I do know. Cool. Combinatorics, factorial, principles of counting, combinations, bijection principle. So interesting. Maybe we'll come into more, come in contact with the more bijections. So I already know one of them, star-bar theorem, and yeah, that one where you have to choose. So like you have to divide a set into 3 or 4 sets or whatever. Then you can, yeah, okay, that thing. I know that bijection, right? And then creating sequences for something that is not directly related to sequences. So sequence of correct, incorrect, something like that, or 1 zeros or something like that, right? Yeah, that would be fun. Combination with repetitions allowed. Permutation, circular permutation, non-identical systems in fixed. Yeah, whatever. We'll do that when we get there. Recurrence relations. Yeah, this is something that I used to do when I was, preparing for Olympiads, although I never actually got the chance to pass it, right? Yeah. But still, this I didn't encounter while for these 2 years. I didn't encounter this thing, but I did do this once. So maybe we can do that. Principle of inclusion and exclusion, right? This is a nice thing. Arrangements, okay. Occupancy problems, fine. Pigeonhole principle. We'll see. We'll see. Midpoint theorem. Really? Why not just Thales theorem? Oh, because that's what they do in 10th standard. That makes sense. They don't have Thales theorem in 10th standard. Oh, there is Thales theorem, but it's later on. Fine. Similar triangles. Okay. You know, the usual geometry stuff. Cool. So let's start. Come on. So we got a preface or something. I'm not gonna do that. Yeah, whatever. First polynomial functions, they got the definition or something. And then they have these rules. F of x plus g of x is a polynomial of degree less than or equal to maximum of n comma m. Makes sense. F of x times, yeah, so we can do that. No big deal. This is a polynomial of degree 4 and 1 is a 0 of the polynomial as this thing. Okay. Oh, they are already using complex numbers. Wow, I didn't think they would do that because I thought it's just the starting of this book. They already are using complex numbers. Wow, weird. Okay, what is this thing? X squared minus square root of 3 minus square root of 2 times x minus, yeah, it's a polynomial of degree 2 and square root 3 is a root of this polynomial. Okay. The above mentioned definitions and examples refer to polynomial functions in one variable. Similarly, polynomials in 2, 3, and okay, variables can be defined. Domain for polynomials and then variables. Okay, division polynomials. Oh yeah, it's just the usual division theorem, right? So the polynomial can be written as the divisor times the quotient plus the remainder, where remainder has less degree than the quotient. Yeah, sorry, than the divisor, right? So then less degree than phi of x. Makes sense. Yeah, well, whatever. Can't be that problematic. We'll see when we get to the questions. Remainder theorem and factor theorem. Yeah, we know that. Uh, keep on going. Fundamental theorem of algebra. So it says that every polynomial can be factored into, linear factors which have zeros as complex numbers, right? And there will be exactly n factors if n is the degree of the polynomial, right? And repeated factors can also be there, right? So, I mean, among those n factors, there can also be some repeated factors. But yeah, that's what it actually says. Okay. Okay, the real numbers of the form are called quadratic surds. In general, square root of a, square root of b, and square root of a plus square root of b, except are quadratic surds. It's okay, but what about them? Okay, if fx is this thing and zeros of this, okay, then can we say that fx has a 0, -1, -2, right? These are just illustrations. Where are the theorems and whatnot? Huh. Since the order of this surd is 2, you may expect the polynomial of lowest degree be polynomial of degree 2. Okay. But square root 5 is a rational, so whatever. Okay. So p of x is ax squared plus bx plus c, and then you're saying like, okay, this is, oh, so that's a really nice method. I mean, just figure out what a, b, c are, right? Using, the irrationality and rationality of, yeah, right, of the coefficients, and then, yeah, we'll see what happens. That should make sense. Cool. Interesting. Okay. Yeah, we'll see that later on. So the required polynomial function is p of x is equal to ax squared minus 5a. Okay, you can find the other zeros of this polynomial, be negative square root 5, well, whatever. You know that the polynomial functions having, say, what n roots can be written as p of x is equal to, okay, fine. And clearly this function is of n degree, hence the coefficients may be rational, real, or complex depending on the zeros, right? If the zero of the polynomial is square root 5, then p of x is equal to x minus square root 5, or a times x minus square root 5. Makes sense. But we want a polynomial with rational coefficients, so we multiply this thing by the conjugate of that, right? Thus we get this polynomial. Interesting. Where the other zero of p of x is negative square root 5. Okay. Obtain a polynomial of lowest degree with integer coefficients whose one of the zeros is square root 5 plus square root of 2. Oh, so now it's like the sum of two cells. Okay, let p of x be equal to x minus, fine. So that's x minus square root of 5 minus square root of 2. Huh. We get p of x is equal to, oh, okay, so you are saying like, right, okay, this is kind of interesting. This is very interesting actually. Right, and then doing all of that, you just get this thing. So here are all the terms with rational coefficients, and these have irrational coefficients, and then you do the same kind of thing once again. So, right, and then you get this thing. So this, right, it might or might not be the minimal polynomial. There might be, some factors that don't want in there or something like that. Oh, so all these are actually irrational. That's weird. Okay. I mean, technically, they should have really factored out and seen if that is in fact the minimal polynomial or not. I mean, if there's some kind of quadratic polynomial that can be factored out with irrational roots and whatever, such that the other part that has this as one of these zeros, right? What about a situation like that? But yeah, over here, as you can see, like the roots are just square root 5 minus square root 2 minus square root 5 plus square root 2 and negative square root 5 negative square root 2, and of course this root as well. Okay, interesting. Yeah, we'll see. Okay, identity theorem. A polynomial of degree n is identically 0 if it vanishes for at least n plus 1 distinct values of x. It's kind of weird. I mean, why is this the minimum? How can we prove that this is the minimal polynomial? And there will be no other polynomial that, yeah. Interesting. So we can easily prove that the minimal polynomial cannot be of degree 2, I guess, right? So we already have polynomial of degree 4 with rational coefficients having this as one of the zeros. We just have to prove that 3 and 2, these two degrees cannot happen, and then you're good to go, right? And let's generalize this thing. So we'll say it's square root of a plus square root of b. So we want, and a, b are just integers, prime integers, right? And we want this to be one of the roots. Okay. So let's start. We want to prove that degree 4 is the minimum degree. So can it be of degree 2? So you got x minus square root of a and then minus square root of b, and this times of x minus alpha, right? This this polynomial, it has rational coefficients, right? This is just expanded as x squared. Then you got, this times that and this times that, so minus of alpha plus square root of a plus square root of b times x, and then plus some other stuff, like just alpha times square root of a plus square root of b. We know that one, right? Yeah. So now this must have only rational coefficients, which means that this is a rational coefficient, so alpha must be of the form some number q minus square root of a minus square root of b, right? But then this also has to be rational coefficient. When you actually multiply out, what you get? You get square root of a plus square root of b times alpha minus, okay, wait, sorry, not alpha, it should be q over there. So q is just some rational number. So q times this stuff, okay, and then minus square root of, yeah, okay, so minus of square root of square root of a plus what am I saying? Square root of a plus square root of b squared, right? So this is already irrational. What about this guy? It's like a plus b minus 2 square root of ab, right? Okay, and then plus square root of a plus square root of b times q. So for this to be rational, what should happen is that this thing must be rational. Now, can this be rational, right? That's the question. Now, if a and b are prime numbers, or yeah, something like that, then that would mean that this is actually, yeah, this will definitely be irrational. There's no way that this can be rational. Yeah, that's what it is. Because square root of a plus, I mean, okay, do I even have to justify that? I think we can see that already. Yeah. So what would happen is if a and b are actually not co-prime? Yeah, what about those cases? What if a and b are equal? Yeah, okay. And then similarly, you can do kind of this analysis for a cubic function, I guess. Right? Yeah. That's very interesting. So that's square root of a and then square root of b or something like that. What about a cubic function? So, okay, exponents of this stuff, and then you got exponents alpha. Hey, did I even say alpha is actually rational, or no? I didn't, but I did, see this, that this should be rational. That's why alpha can be written in this form. That's valid, right? Okay, that is this thing. So can we prove that this is always going to be irrational? What are our assumptions? Our assumptions were that a and b are not reducible anymore. That is, those don't have any more square factors in them. Okay, and a, b don't have a GCD. That is, they are co-prime, right? What would happen if they were not co-prime? Yeah, then you can just take that GCD out or something. Okay, that's kind of weird. They could have a GCD, right? That is a possibility, but of course they cannot be equal, right? There's got to be some difference between them, right? And probably that's what's going to cause these terms to all not combine into a rational number, basically. This is kind of hard to explain. We'll see when we get there. So of course, like degree 2, it's not valid. What about a degree 3? So if there's a degree 3 minimal polynomial which has this as one of its root, right? Then you can just write this polynomial as, you know, x minus something times that polynomial, right? Of course. And because that polynomial only has rational roots everywhere, that so x minus something, that other root, that must be rational as well, because if it's not, then yeah, you're going to get some problematic stuff going on. So that must be rational, right? Yeah, but as you can see, we don't have actually any rational roots, and that's why, yeah, that makes sense. And wait a second, you got a cubic that, hey, so every cubic has at least one root, so it can already be written as x minus something, and that times some kind of quadratic, right? Yeah, cubic always has one real root, so we already got one root we know. So you got x minus square root of a minus square root of b, and that times some kind of quadratic. Yeah, that's the thing. That's what's happening, right? Okay, and that quadratic must have irrational numbers. It's getting complicated, isn't it? I mean, we did prove that it cannot happen, but yeah, just extend this to, you know, all of these things. So x minus square root of a minus square root of b, and then that times x minus square root of a plus square root of b, and then you get this thing, and then do the same thing, right? You know, whatever this thing is, sure. So this same stuff, and then you got, so instead of just minus 2 square root of 5, just gotta put plus 2 square root of 5, and then do the same thing. And I'm guessing I'm just going to get square root of a minus square root of b, and then minus square root of a plus square root of b, and minus square root of a minus square root of b, and square root of a plus square root of b. Those as our zeros. If I do get those things, then it's very clear that all those are just irrational, which means, yeah, this actually is going to work. This is the minimal polynomial all of the time. That's awesome, isn't it? Yeah, okay. That was nice. What else? Identity theorem. A polynomial of degree n is identically 0 if it vanishes for at least n plus 1 distinct values of x. Oh, yeah, of course. So, right. We know that f of x can be assumed to be this thing. So if it has degree n, then it can be thought of as this thing, right? We assume its degree is n. Yeah. I mean, they are saying polynomial of degree n, but the actual thing wherever we will be actually using this is with the assumption that this might have degree n or less. Makes sense? Yeah. And then we will assume that it will be of this form, but then because you got n plus 1 distinct values of x, yeah, there are actually supposed to be n plus 1 zeros. If a is not 0, then there will be n plus 1 zeros, right? But that doesn't make any sense because there are at max n distinct zeros, right? So yeah, a must be 0. That's the only way out. Okay. What's this thing? Let alpha n plus 1 be the n plus 1th value of x at which f of x vanishes, then f of alpha n plus 1, that's equal to 0. Okay, but then this is going to happen, right? One of them must be 0. So alpha n plus 1 cannot be different from all of these, right? And if it is different, then a must be 0. That's the only way. Makes sense? Yeah. And what do we have? Using the above results, we can say that if two polynomials of degree m and respectively have equal values of n plus 1 distinct values of x. Okay. Oh, equal values at n plus 1 distinct values of x, then they must be equal. Yeah, I guess that makes sense. Yeah, their proof is also good. I understand that. Corollary. Corollary, whatever. The only periodic polynomial function, periodic, I mean that gives it away, it's at infinite points that it is becoming 0 or whatever, it becoming equal to a constant or whatever, right? Yeah, So the only way is that it must be a constant polynomial. Sure. So at some point you got some value after a period, you still got the same value, and then so on, right? So for infinite numbers, you just got the same value, and then that just means that p of x is equal to a constant polynomial, right? Because p of x minus that constant, that polynomial of degree n, supposedly degree n, that has infinite number of roots. Yeah. Okay. Let p of x be polynomial such that x times p of x minus 1 is equal to x minus 4 times p of x. Ooh, interesting. For all x belong to real, find all such x. Wait, this is for all x. That just means like it's an identity. Okay. Wait. What you're saying is like this left hand side, this polynomial, it actually has 4 as a root. Wait. Wow, that's interesting. So when you put x is equal to 4 into this whole thing, what will you get? Like 4 p of 3 is equal to 0. So 3 is actually a 0 of the polynomial p. So you can already guess that p of x is, and then similarly you can just do the same thing for the right hand side. And you can say, okay, 0 is also a polynomial. So, sorry, 0 is also a root. Makes sense? Right. So that's basically saying that p of x is equal to x minus 3, or I should just say a times x minus 3, right? Yeah, I guess so. Okay. Times some other polynomial, which will just say q of x. Let's put that in here and let's see what we get. So it's going to be just x times a times what is x? Oh, yeah, instead of x, you actually have to put x minus 1 because p of x minus 1 is what we have on the left hand side. So you got x minus 1, and then you got x minus 4 times q of x minus 1. This thing is equal to, so you got x minus 4 times p of x, which is x minus 4 times a times x minus 3 times q of x, right? And this is for all values of x, right? That's interesting. Wait a second, this is very interesting. What does that mean? That just actually means that, you know, x minus 1, x minus 4, these are also zeros of q of x, and then you can keep going like that. Wait, this is very weird. Uh, yeah, this is very weird. Oh god, oh god. We already got that 0, right? X equal to 0 is a 0 of this polynomial, right? Okay. But then what about p of 1? If I put x equal to 1 in there, I'm going to get x p of 0, which is 0, is equal to, oh, I see, that's a loophole in there, isn't it? So you got 1 times p of 0, so 1 minus 1 is 0, is equal to negative 3, whatever is there, we don't care about that. And then you got p of 1, right? But what that means is like p of 1 is also 0, and then you can keep on going. So p of 2 will also be 0, p of 3 will also be 0, p of 4 we can't conclude anything because this will actually become 0, right? But from here we already know that actually that 3 is actually yeah, the 3 is something that you can put in that. Okay, we already know that. You don't have to. You can't put 3, unfortunately. You can put 4 though. So just put. Oh, come on, that's not helping, is it? Right. That's not helping. Okay, all it's saying is that 1, 2. Hey, you can also go the opposite way, right? So 0 is a root, then just put x equal to 0. Okay, that's just weird. Don't do that. Oh god. What about negative 1? P of negative 2 and stuff over there. Oh, that's weird. You don't want to be doing that. That's not going to help you. I thought I would just get a bunch of, you know, yeah, loop stuffs, and that will do it. So not x and x minus 3, you also got some other roots. So you got x minus 1 as well. You also got, because 1 was the 0, you got 2 as the thing as well. So just put those in there, you know. So if it is not 0 everywhere, then it just got ax times x minus 1 times x minus 2 times x minus 3 times q of x, right? That's what p actually is. So then x times of this thing, but with x minus 1 in there, that's just going to be like a x minus 1 times x, and you got like x minus 2 or something. Interesting. You got like this thing. So you got x, then you got x minus 1. So this guy becomes this thing, then x minus 2, x minus 3, x minus 4, q of x. So if it's not 0 everywhere, then you can write it like this thing. And we'll just say q is a monic polynomial, right? Because a can be anything we want. And this is equal to x minus 4 times p of x. So you got, look, I'm not looking at the solution, right? So my method would be different than theirs, I guess. You got x minus 4, just put all of this stuff in there. Okay, not all of this stuff, this stuff. Cool. So it's gonna be just x minus 1, x minus 2, x minus 3, and x minus 4 as well. Yeah, and then q of x. Does that make, oh, hey, that's, no, but the thing is x minus 1 is there. Oh, but if this is true for all real values of x, then that just means like these two must be the same. That's the only way out, isn't it? For all real values of x. So you got two polynomials. Yeah, I mean, this is a polynomial, that's a polynomial of the same degree, but then, right, just call q of x minus 1 as a new polynomial. We'll call it as r of x. So r of x is equal to q of x. They have the same degree, but it's a finite degree, right? That's what we assume. And this is actually true. This equation is true for infinite number of values of x, basically. So what does that mean? Yeah, that these are in fact the same polynomial, right? Exactly. Yeah, okay, that's cool. So, you know, this polynomial, I mean, that was obvious. They are the same polynomial, of course. Huh. Plus 1, and you got q of x. That's very weird. Why is this happening? And you just get back the same thing. But that should not happen. All the zeros. So q of x can be written as, you know, the product of x minus alpha I, right? Where alpha I are the zeros. But then x minus 1, when you put that in there, it's going to be minus alpha I minus 1, right? So clearly, the polynomial will change because the sum of the zeros will now become a different thing, right? So that linear term, okay, I should say the second leading term. Yeah, that's better. The second leading term, that will change. But over here, it's still the same thing. Yeah, how can that even happen? Doesn't make any sense, right? So that's a contradiction. And that just means that a has to be 0. There's no other way. Yeah, so like p of x has to be 0. Huh, that was a big proof. What do they have? Find all such p of x. It's only a 0 polynomial. Okay, q of x periodic. So constant. Oh, that would have also worked. It's just a constant, not necessarily 0. Ah, why did I not think of that? So in this case, the constant would just be 1, right? Because we assumed this to be monic polynomial, right? Yeah, right. That makes sense. Of course, it's a periodic. That's what this equation is saying. Q of x is equal to q of x minus 1. That just says q of x plus 1 is equal to q of x. Guess what's the period? 1 is the period. A polynomial function that's also periodic, that's just a constant function. So q of x is a constant. Not necessarily 0, just a constant. So our p of x just becomes a times x minus 1 and all that stuff, right? Yeah. And that's what they got. Okay. Man, I have to be really careful. I really thought this would be 0. It's not always 0. It could also be constant. Okay, now I understand this thing. Let p of x be a monic cubic equation such that p of 1 is equal to p of 1 equal to 1, p of 2 is equal to 2. Yeah, I think I've seen this kind of question once. So they give a kind of a pattern, right? Maybe we can write that as, yeah. So this as a proper rule or something, we'll just say p of x is equal to, right, it's a monic polynomial cubic equation. Okay, so a monic cubic polynomial, not equation. There's no equal to sign. Okay, so like this happens. This is for 1, 2, 3, 4. Oh, you don't have this guy's value actually, right? Whatever. So p of x is equal to x for x belonging to this set 1, 2, 3, right? But what that means is like p of x minus x. This thing is equal to 0 for these three values, which means these three are the zeros of this polynomial, right? So this polynomial can be written as a times of x minus 1 times x minus 2 times x minus 3. Because it's cubic and oh, it's a monic cubic. Perfect. This has to be just 1 because p of x would basically be x plus this guy, right? Okay. Yeah, because p of x minus x was this. It was also monic polynomial, right? Monic cubic polynomial because this is actually a linear term. Makes sense. So it's just equal to this thing, and then just figure out what p of 4 is. So like 4 plus 1 times 2 times 3, I guess, which is 10. So 10 will be the answer. Cool. Next question. Okay. So our first exercise, right? You got 11 questions. Let's do them. The first question. Okay, find a fourth degree equation with rational coefficients, one of whose roots is this thing. So once again, very similar to what we saw previously, I'm going to do the same method. So first we'll just do x minus square root 3 minus square root of 7. Okay, but that times x minus square root of 3 plus square root of 7, right? Yeah, and this will just give us this guy's square is like x squared minus 2 square root 3 of x plus 3 and minus 7, which is x squared minus 4 minus 2 square root 3 of x, right? Clearly, x is equal to square root 3 plus 7, square root of 7, and square root 3 minus square root of 7. Both are zeros of this already because we are using this. Yeah, okay. This thing, yeah, will multiply with this thing, yet another polynomial. So a polynomial like this, x squared minus 4 plus 2 square root 3x. And now this will give us a biquadratic. Oh, hey, just want a fourth degree equation with rational coefficients. Hey, that was actually much easier than what I thought. Huh, easy, isn't it? Fine. I mean, I thought you would have to figure out the minimal polynomial or something, but no, just the fourth degree polynomial. Cool. So you got x power 4 minus, oh yeah, and by the way, this guy, what about this guy, huh? So it's x squared minus 4, just like that. But now you got plus 2 square root 3. This is, of course, coming from this thing. So if this was x plus square root 3, then it would give us this guy, right? Makes sense? Cool. So this will actually have the zeros as negative square root 3 and plus square root of 7 and negative square root 3, negative square root of 7, right? So all four roots are irrational. You can clearly see that, right? And then using the same logic that I showed previously, yeah, you can just say that this is actually going to be the minimum degree polynomial, right? Exactly. Because if there was a cubic polynomial which was a minimal degree polynomial, that would just mean this thing can be written as x minus alpha times the cubic polynomial. But then alpha can only be among these things, and none of these are rational, so this cannot happen. So a cubic polynomial cannot be the minimal polynomial. However, a quadratic polynomial will be already proved that's not possible. So yeah, that basically means the fourth degree polynomial is the minimal polynomial. Cool. And also we don't actually have to figure out the minimal polynomial, but whatever. I actually, had to deal with questions like this when I was preparing for Olympiads. Yeah, I got unlucky. I never got into. Yeah, well, whatever. Just move on. Okay. So you got this thing to square that x power 4 minus 8x squared plus 16 minus square of this guy, just 4 times 3 is like 12, well, x squared, there we go. So x power 4 minus 20x squared plus 16. That should be cool. So that's the polynomial that we got. Nice. Okay, hopefully it's correct. make any kind of mistake. Find a polynomial equation of the lowest degree with rational coefficients whose one root is, oh god, you got cube roots now. That's interesting. So yeah, okay. Cubing is not that easy actually. Cube root of 2 plus 3 cube root of 4. Why? This is very weird. Maybe there's some other method than doing that. Because so for square roots it was pretty easy. But then for cube roots, yeah, it's gonna be very complicated. Okay, we could do this. We could just say x minus 3 cube root of 4, that's u. So it's got u minus cube root of 2, and then if you want to multiply by something to dissolve these things, like u first. So it would just be like u cube is equal to 2, right? That will be the polynomial that you get. Yeah, because there's really no other way of dissolving this. Yeah, this cube root. You could multiply by this thing u square plus cube root of 4 times u plus whatever, but then this has complex roots and everything, and yeah, that's complicated, isn't it? That's so you got u cube is equal to 2. That's the thing. This is going to give us something of the form x cube plus some irrational terms, yeah, which will also contain cube roots. So we will get at least a 9th degree polynomial. Oh god, this is very weird. That's not helping. Something else that you can do. Rational coefficients whose one root is. We want the lowest degree, huh? Okay, I'm thinking of something. It's much different to what they are doing, but let's try it out. So we'll just say x is equal to cube root of 2 plus, I'm just gonna do the exponents on this guy, and we'll see if we can somehow match them up to get 0, basically, right? So a linear combination of them, and then we get 0. If that can happen, it would be really cool, isn't it? Cool. So you got what? 3 cube root of 4. Oops, cube root of 4. Okay. Well, x squared only won't work, but we'll still try it out. Almost. Oh, yeah, it just won't work. I know that, but let's keep on going. Something nice can happen. So cube root of 4 plus 2 times of that times that. So 6 times the cube root of 8. That's like 6 times 2 is just 12. Okay. Plus, interesting. And then this guy like squared. Cool. So you got 9 cube root of 16, which is 18 cube root of 2. Okay, so from that what we got is x squared minus 12 is just equal to, or whatever, just keep it like that. Who really cares about that? So it's what? 18 cube root of 2 plus cube root of 4, right? Plus 12, basically. That's kind of nice. Yeah. Okay. And then I'm thinking, what about cubing this? So the cube of this guy. Oh god, that's kind of complicated. So you already got 1, which is equal to 1. So you can scale that up and make it 12 or something or whatever. Is this actually enough to, combine these and get some stuff done? No, it's not, unfortunately. That's interesting. Yeah, like, I don't know. Eliminating these quantities somehow, right? That's what we look for. Eliminating these quantities. That's not an easy task. We probably have to look for cube root, so sorry, the cube of this thing. You of course would need to do that, right? In that case, you will actually have like 3 vectors if you think about it. Yeah, I will explain what I'm thinking later, but first let's just figure out the cube. Yeah, okay, so what's the cube of this? Yeah, just got this guy cubed, which is 2 plus 3 times of this guy squared, which is the cube root of 4 times this guy. So you got 3 cube root of 4. Okay, and then you got plus 3 times just this guy. Yeah, cube root of 2 times this guy squared. So you got 9 cube root of 16. Nice. And then you got plus this guy cubed. So you got 27 times 4. Cool. So you got 2 and then this guy. We have to calculate that, don't we? 2 plus, what's this thing? 8 and then you got 28, which is 108. Okay. Plus, so you got 9 and then you got cube root of 16, which can be written as cube root of 8 times 2. So you got 9 times 2, which is 18. 18 cube root 2. Okay. And then plus this guy, you got like 27 times. So cube root of what? Cube root of 32, right? So 2 power 3 times 2 power 2. It's going to be just 2 times 2. Yeah, like cube root of 4, of course. That should do it. So you got 54 cube root of 4. Let's write that down. So it is 18 cube root of 2 plus 54 cube root of 4. Okay. And then plus this guy, which is just 1, 0. Makes sense. Right. Now what we need to do is figure out a combination of these guys such that all these radicals would get cancelled. Yeah. Okay, that's interesting. So right, and like these are not collinear. It's not collinear with any of these. Okay, it's doable. Don't worry, we can do this for sure. Okay, now think about it. We have to get rid. I'm just gonna say, okay, a times of this, b times of that. So you got a plus 18b, that's equal to 18. Interesting. And then you got 3a plus b is equal to 54. That's interesting. Okay. When does this happen? What's 18 times 3? It's 3 times 24 is just, wow. Wow. B equal to 0, a equal to 18. That should do it. That should do it. 18 is equal to 18. That's 0. 54. Cool. So what we do is, don't take this. Wow. Okay. No, I didn't think this would go out like that. What happened? Like cubing this, we got, it's just 18 times that. Why? Why after cubing this, we got this thing? It's basically saying like x cubed is just equal to 18x because that's what x is. And then that thing plus 110. We already got a polynomial in that case. But why is this the case? X cubed is equal to 18x plus 110. Once again, what was x cubed? Let's just do this correctly this time. Maybe we slipped somewhere. So, right. It's this guy, cube root of 2 plus 3 times, or let's just say it's 2 power 1/3 for convenience. And then 3 times 2 power 2/3 and all of that cubed, right? Yeah. Interesting. Well, if you take some stuff out, so like what about we take 2 power 1/3 out, then this can be written as 2 and then you got 1 plus 3 times 2 power 1/3, that guy cubed, right? Okay, so this will be like 2 times, so 1 plus 3 times this stuff, which is 9 times 2 power 1/3 plus 3 times this thing squared, so you got 27 times 2 power 2/3 and then plus this thing cubed, and you get 9 times, oh yeah, you are going to get the thing. Wow, unexpected, but fine. Cube of that, 27 times 2 cubed, okay, just 2 cube rooted cubed, so 27 times 2 is going to be 54. Nice. So 55 times 2 is just 110 as we expected. Then you got 18 cube root of 2 and then 54 cube root of 4. Exactly, that's what we got. So what does that mean? This is the thing. X cube is equal to 18x plus 110. So yeah, that should be the thing, of course. Of course, that's got to be the thing. So just with x and x square, any kind of linear combination, you can't eliminate both of these radicals simultaneously. You have to take the care of, you have to go to x cube to actually do this thing. So that explains everything, right? That explains why this is the minimal polynomial and everything. Yeah, okay, cool. So we got the thing. X cube minus 18x minus 110. Yeah. That's the equation. Cool. Next. Third is form the equation of the lowest degree with rational coefficients which has this and that as two of its roots. So the first is usually much easy. It's just x minus 2 squared is equal to square root of 3, right? Yeah. So x squared, minus 4x. Ooh, I should say this guy squared, well, whatever. And then plus 4 is equal to 3. So x squared minus 4x plus 1 is equal to 0. That's this equation, right? What was I doing once again? The lowest degree with rational coefficients, which has this as two of its roots. Ooh, that's interesting. That's square root 2 over there. Wow. Come on, think about it. Is this the right method to do that? I'm gonna get a 4th degree equation. Are we sure it's correct? Lowest degree was said with rational coefficients. So the 4th degree, right? There has got to be at least a 2 degree because you only got 2 roots. Can it not be a 3rd degree equation? No, it cannot be because, right, I mean, it's the same thing as what we did previously. Like, okay, if you got x minus this and x minus that, then the equation that you'll get, right, the lowest degree equation without rational roots, is gonna get x squared minus 5 plus square root of 2 plus square root of 3 times x, right, plus multiplication of these guys, which is 6 plus square root of 6 plus 3 square root of 3 plus 2 square root of 2, right? And then what should happen is that you just multiply this thing x minus alpha or x plus alpha or whatever. X minus alpha is better. And yeah, and then finally you just get this thing 5 plus square root of 2 plus square root of 3 times x squared, and then you got x cube over here using beta's formula and whatever, right? And this must be a rational number. What does that mean? Alpha has to be of the form minus square root of 2 minus square root of 3 plus q, and then do the same thing over there. So you're gonna put that in there, and yeah, I can already see it's not going to work. It just won't work. Of course, there's no way it's going to work. There should be some kind of like a complete theory only dealing with radical powers of integers and how they behave, but we don't have that. Whatever. So you got this thing, and you will multiply that with this and hope to get something nice out of it. Wow, that's weird. There's zero hope for us in that scenario. How am I going to do that, right? Yeah, just do it if that turns out to be a rational number for some q, some rational q, then you're good to go, right? Then the 3rd degree equation, that would work. But I think the 4th degree equation is what's the thing, because we don't want to do all that. Yeah. Okay, so skip that. Let's go to the 4th degree equation. So you got this equation which has 2 minus square root 3 as one of the roots. Oops, 2. Oh, it's gonna be negative square root 3 anyway. We don't care about that. No, actually it is 2 plus square root 3. Cool. And then 3 plus square root 2, right? Okay, cool. It's got like x minus 3 squared is equal to 2. So x squared minus 6x plus 7 is equal to 0. These two just multiply this out. Yeah, that should do it. So this times that, it's like x power 4 minus 6x cubed plus 7x squared, and then you got minus 4x times that, so minus 4x cubed, 10 plus 24x squared, and minus 28x. This times that is x squared minus 6x plus 7, right? Okay, which in combination is going to be x power 4 minus 10x cubed plus 31x squared, oh shit, 32x squared, minus 34x plus 7. Is that the thing? Hopefully. So got x power 4 minus 10x cubed plus is 32x squared minus 34x plus 7. Okay, next, fourth. I never thought that something like this would be time consuming, but it is. Show that this thing is a factor of that. So x minus 1 squared. Oh, just x minus 1 would be easy. Got x minus 1 squared. That's interesting. Okay, that's a factor of this guy. So, okay, like 1 minus n plus. Yeah, you can factor out x minus 1 from there, something like that. I guess we can. So this can be written as x minus 1 times. Well, actually, I should do it correctly. So what do you got? You got x power n. Okay, just got minus x, and then the other stuff is, so I have plus x, right? So minus of n minus 1 times x plus n minus 1. This will be x times x minus 1 minus 1 basically. Yeah. So x times x power n minus 1 minus 1 minus n minus 1 times x minus 1. That's basically x minus 1 times, now you can take x out, and then x minus 1 of, yeah, that's gone. Now you're gonna have n minus 1 roots, so x power n minus 2 is where it starts. Wow, that's weird and interesting. Okay, just keep on going like that, and you will eventually get to something. Or you could just have gone with this x power n minus 1 first. Yeah, why not do that? So let's be like x minus 1, x power n minus 1 plus x power n minus 2, and so on till 1. That's this thing when you factor out x minus 1 from there. And then when you factor that out, it's going to be minus n. So that's x minus 1, and then you got all of these can be paired up, right? Yeah, so n can be broken down like this, because there are exactly n terms. And then this term has an x minus 1 factor, this also has an x minus 1 factor, this, yeah, you get that, that's just 0. Okay, so it has x minus 1 inside of it as well, and that times some stuff we don't care about, polynomial stuff. Yeah, so x minus 1 squared, it's a factor. Cool. So fourth done. Fifth is if a, b, c, d, e are all zeros of the polynomial, this polynomial, find the value of 1 plus a times 1 plus b times 1 plus c plus 1. Okay, I get it. Wait a second. Just make this negative a, so negative 1 minus a, and then you got, yeah, these are all zeros of this polynomial, isn't it? I get it. Negative 1, negative b, and so on, right? How many are there? There are 5 of these, so you actually have to put a negative like this, and then you get the thing. Just keep on going. This is basically like this, right? We're just gonna define this polynomial f of x is equal to so 1/6 of this whole thing, right? 6x power 5, and whatever was given to us. Cool. And this thing, this whole thing can actually be written as x minus a, x minus b, and so on. So when you put negative 1 in there, just get this expression. So this whole thing is pretty much just negative f of negative 1, and that is easy to figure out. Just put negative 1 there. So negative of 1/6, then you got what, 6. Okay, that's negative 6 actually, because negative 1 is what we should put. Negative 6 plus 5, then negative 4, positive 3, minus 2, and plus 1. But whatever. Hey, that looks so familiar. Okay, whatever. Yeah, it's like the derivative of, oh, of course, I should have known. This is the, okay, we don't use calculus for this. Yeah, no need to bring in the machine gun. It's actually doable just like this. So no need to go for calculus or whatever. Okay, just negative 1 upon 6. You got negative 1, negative 1, negative 1. So negative 3. Right, it's gonna be just 1 upon 2. That's the thing. So the value is just 1 upon 2. Right? Right? Or not? It should be. What could go wrong over here? Nothing as far as I know. Okay. So 1 upon 2 is the thing. Next. Sixth question. Sorry. Okay. Fifth is, wait, that was the fifth. Sixth question. If these are the roots of this equation, show that n is equal to 1 minus alpha, okay, of this equation, right? So basically all the complex roots, fine. Complex nth roots of unity are these guys, and then 1 is there, of course. Show that n is equal to 1 minus alpha. Come on, it's just like, yeah, we know the thing. Just get rid of this x minus 1 factor. You're just gonna get x power n minus 1 plus x power n minus 2 and so on all the way to 1. This polynomial has alpha 1, alpha 2, alpha all the way to alpha n minus 1. Those as its zeros, all distinct and whatever. And just put 1 in there. That's right. That's gonna give us this expression. Come on, do the thing by yourself. I won't explain that. She's gonna get n as the value. That was easy to prove. What was that? Okay, next, seventh is if alpha, beta, gamma, delta are the roots of this expression, show that 1 plus alpha square, 1 plus, interesting, the squares of these guys, huh? Oh, yeah, that's equal to 1 minus q plus s squared plus p minus r squared, huh? Okay. Wow. The squares of these guys. You could, just expand this, right? Sure. So you can first of all just think about, think about like using Veta's formula or something like that. Yeah, but you got squares. It won't be easy to do everything. Hey, I know a way of doing this. This might be weird, but you gotta try it out. So alpha squared plus 1, that can be written as alpha plus iota times alpha minus iota, right? So this whole thing, because there are only 4 of these, I can invert and stuff and then just write this as, iota minus alpha and then iota plus alpha and stuff like that. Okay, and then I can take out -1 factors from all of these guys, and yeah, basically just write this as negative alpha times iota minus alpha, and then negative iota, negative beta, and okay, this is not supposed to be there, and iota minus beta and so on, right? So the other 2 factors as well. And guess what is this thing? Yeah, it's just f of negative iota. Just put that in there, and that's just f of iota. So once you do those things, just multiply them together. It can't be that hard, can it be? Just put iota over there and negative iota and multiply. So what happens when you put iota in there? Just get like what, 1 minus p iota minus q, then you got plus r iota plus s, right? And this can be written as 1 plus s minus q. You got all this stuff, right? Okay, which is just plus r minus p times iota. Now when you put negative iota, you will get pretty much the same stuff, except instead of wherever you got iota, the odd powers, those will just give negative of whatever we got previously. Make sense? So that will just be negative of r minus p times iota. And then when you multiply this together, it's gonna be like this guy squared and plus this guy squared, and no iota involved. Cool. And yeah, that's what we got. 1 minus q plus s squared plus p minus r squared minus p squared. Same stuff. So 7th, sure, that makes sense. Did it. Next. 8th. 8th is if f of x is equal to x power 4 plus ax cube plus bx squared plus cx plus e. And it's a polynomial such that f of 1 is equal to 10, f of 2 equal to 20, f of 3 equal to 30, then find the value of this whole thing. Okay, so once again, another pattern over here. So f of 1 is equal to 10, 20, then 30. So you can see f of x is equal to 10x for these 3 numbers. So f of x minus 10x, right? That's, well, that's a biquadratic, isn't it? Sure. A monic biquadratic at that. It's already got, like, what are the zeros that it has? It has 3 zeros, 3 known zeros, which are x is equal to 1, x is equal to 2, and x is equal to 3. So we can actually write this monic biquadratic, so f of x minus 10x, that can be written as x minus 1, x minus 2, x minus 3, but another root that we don't know. So this whole thing, right, f of x just becomes 10x plus this stuff, right, x minus 1, x minus 2, x minus 3, and x minus alpha. Okay, what else is given to us? Right, Find the value of f of 12 plus f of that's the all the information you gave us. There's just like 3 pieces of information, nothing else. Whatever. And then you want to figure out what is f of 12 plus f of negative 18, that upon 10. How does that even make sense? 12 negative 18. Why? Okay, don't question, just do it. So first 10 times 12 minus 18, sorry, 12 minus 8, that upon 10, right? That will just be 4 upon 10. So it's like just 4 over here. That's 4 plus, okay, so first we'll just put 10. So you will have 9 times 8 times 7 times, okay, then plus f of negative 8. So plus negative 9 times, what is this? Negative 10, and that times, what is this? Oh wait, it's 12, not 10. Sorry, I messed up there. So when you put 12, it's going to be 11 and 10 and 9 and 12 as alpha. When you put that, you're gonna get plus, and then you got negative what? That's negative 9, then negative 10 and negative 11. That's cool. I thought it would be like this. And then you got negative 8 minus alpha, whatever. Thing is, like, you got 3 odd, okay, you got odd number of negatives, make that come out, negative of that guy, and then all of that upon 10, of course, right? Yeah, that cancels. So yeah, it's like 9 times 11, and then this thing minus that thing, so just 20, and that cancels. Cool. So alpha we don't even need to know, it just cancels right away. That should be the thing. Yep, that should be the thing. Cool. So this is the thing, right? 20 times 9 times 11, so that's gonna be, 180 times 11 is like 19, oh god, 1980, and I think plus 4 is 1984. Next, is that some kind of year date? I don't know. Maybe that's the year when this question was brought up. 9th. The polynomial, this polynomial is not divisible by x squared plus x plus 1. So find the value of k belonging to natural numbers. Okay, this is not divisible by that. So what do we do? Okay, figure out the value of k belonging to natural numbers. Interesting. You want x power 2k plus 1 plus x plus 1 to the power of 2k. You could just, yeah, right. Okay, I see what's happening over here. So it's not divisible. What we just have to show is that this whole polynomial is called as p of x. This can be written as x squared plus x plus 1 times q of x plus r of x, where r of x is not equal to 0 and it has degree 1 or less. It could also be constant, right? So yeah, we just have to look for this thing. If it's not 0, then just put one of these guys, just put omega, that's the first cubic root of unity, into this expression. You will get 0 over here. This will, if it turns out to be something that is non-zero, right, then you are basically done, right? No big deal. That would just mean this is not equal to 0, because if it's equal to 0, then this must be 0, and this is not. Yeah, you get the idea, don't you? So just put omega in there. So you got omega power 2k plus 1, and then omega plus, oh, and by the way, omega is just e power 2 pi, e power I 2 pi upon 3. Come on, I don't want to use complex numbers, but then whatever. And that thing using the Euler's theorem can be written as negative 1 upon 2 plus square root 3 upon 2 iota. So that thing plus, where did that go? Plus 1, that's like 1 upon 2 plus square root 3 upon 2 iota, which is like e power I pi upon 3. But that thing to the power of 2k, right? You see what's happening? It's just 1 plus e power I 2 pi upon 3 times k. So that's what I got from here. So yeah, okay. And then plus, so from this guy, x power 2k, I just got this thing. e power I 4 pi upon 3 the power of k, right? And then, using our GP formula, this just turns out to be e power I 3 terms, and then the ratio is just 2 pi upon 3, it's like 2 pi k minus 1 upon the ratio is just this guy minus 1. Of course, for all of this to make sense, k should be, oh, okay, interesting. I didn't think it would be like this, but it is. So it's not divisible by, okay. That's weird. How do you even know that this actually is going to be something that is not using complex numbers? It could be using complex numbers, right? Okay, so we'll have to check for both of them. Okay. Anyway, so when you put omega in there, you just get this guy. What happens when you put negative omega square in there, right? That's what I should say. This is going to be negative 1 upon 2, negative square root 3 upon 2 iota, but then when you do plus 1 for this, it's just going to be this guy, which is, it's just e power negative I pi upon 3, right? Yeah. And then you are just raising that to the power of 2k, so it's just e power negative iota 2 pi upon 3 times k, right? Cool. But then this thing can be done as, pi minus 2 pi upon 3 or something like that. Okay, it's negative already. So you can just, add 2 pi k, right? So this thing plus iota 2 pi k. Because e power I 2 pi k, that's just going to be equal to 1. So it doesn't really change anything. And then this whole thing can be just e power I 4 pi upon 3k. So that just turns out to be that. Cool. So 1 plus e power I 4 pi upon 3k, that's what we got from this guy. And then x power 2k, that's going to be just e power I 8 pi upon 3k. But then you know the deal, you can actually reduce that. You can write this as 2 pi plus 2 pi upon 3k. So both actually give us the same thing. That's awesome, right? Yeah. So both give us the same thing, huh? Which means that the linear term must be 0. Isn't that right? If your remainder is of the form ax plus b, yeah, and when you put two different numbers, it still gives like both give the same thing. That only means a has to be 0. There's no other way around it. Sure. And b is just whatever this thing is. So that's what b is. So it was complex and everything. Makes sense. But the main thing is that this is 0 if k is not equal to some multiple of 3, but if k is equal to a multiple of 3, then this just turns out to be 3, right? That makes sense. Okay. So if this is not divisible by this thing, that just means this has to be non-zero, so k must be a multiple of 3. So 3 divides k. Find the value of k. Okay, if you want value of k, you could just say k is equal to 3m, where m belongs to natural numbers. That should be doing it. Next question. I didn't think it would involve complex analysis. Sorry, it's not analysis, it's just normal complex numbers or whatever. Yeah, next question. Find all the polynomials with real coefficients such that this, hey, isn't that kind of like what we got previously? Huh, weird. So x minus 8, and then that makes sense. So right, when you put x equal to 8, you just get p of 8 over here and then like some other stuff. So 8 is a 0, understandable. What else? Why is this 8 times of that? Okay, when you put x equal to 1, you just get p of 2 to be equal to 0, right? So 2 is a 0, 8 is a 0. Anything else that you can get from that? So 2 is a 0, right? So when you put 2 over here, you'll just get like 4 is a 0. Wait a second. So what did we get? We get 8 and 2. Those are zeros. Exactly. Yeah. So now what we can do is, okay, just put 2 as x in this whole equation. Then just get, you're gonna get like 2 minus 8 is, you know what? I know another better way. Just put x is equal to 1. So like p of 2 will be what we get over here, and then some other stuff. It's going to be 0. And oh, that's going to be 0 as well. Yeah, that didn't turn out to be that good. Oof. So you can't go down, unfortunately. You have to go up. But that's basically telling that 4 is also 0. So 2, 4, 8. We already got these three zeros. Sure. So then p of x can be written as a times x minus 2, and you get the idea, right? Okay. Let's try it out. Okay. So a x minus 8 times 2x minus 2 times 2x minus 4 and then 2x minus 8, right? And that times the other polynomial cube but with 2x inside it, that's equal to 8a. And then you got x minus 1. Okay. And what else? You will just have x minus 2 and x minus 4 and x minus 8. And q of x. Yeah, just wait a second. Okay, that's the thing. Now, right, if p is not 0, so assuming that p is not 0, you can cancel these out. And this is supposed to happen for all real numbers. Then, you know, start canceling some stuff out. So x minus 8 can be cancelled. This whole thing can be thought of as 8 times of x minus 1 times x minus 2 times x minus 4, right? That's what these three terms give us. But then these are identical to these three terms. So like, okay, this whole stuff can be cancelled along with 8. So all you are getting is that q of 2x is equal to q of x, right? And this is true for all real values of x. But right, so if you know, for some, so basically what that is like, q is a constant function, of course. That's the only way this can actually happen. Yeah, because how many places will q be the same value? So like q of x minus c, right? That will have infinite number of zeros. Basically, that's what happens. That just means that this must be a constant polynomial, right? Equal to that constant all of the time. That's the only way. Right. So there we go. Our p is just of this form. It's a constant. And then, you know, since you have this a and stuff, you can assume q to be monic or whatever, right? So the thing really is that p is just equal to a constant times x minus 2 and then you got x minus 4, x minus 8. That should be doing it. Yeah. That's what p is. So you got all polynomials, right? And yeah, that should do it. So p is of the forms, and you know what? Actually, you can also assume that c goes from all real numbers because 0 is also allowed, right? That will also satisfy this equation. So that makes this as our answer. X minus 2, x minus 4, and x minus 8. C is any constant. So anything from the complex plane, it will work. Next. 11th. 11th is let x minus 1 cube divide this thing, and this thing divides this. Okay, find the polynomial p of x of degree 5. Wow. So p of x can be given as -1 plus some q of x. Okay, maybe I should say a of x. Maybe that's not the best thing to. M of x, yeah, m of x, that's a polynomial. That times x minus 1 cubed, right? Okay, and p is of degree 5, so m is a quadratic polynomial, understandable. And u of x minus 1 now. Okay. Oh, come on, think about it. What I'm starting to think of is, you know, since the quadratic polynomial, what would happen if I put negative x over there or something like that? No, don't do that. I don't think that's going to help us. But, you know, let's keep on searching for something. So this can be written as 1 plus n of x, but that's another polynomial, and then x minus 1 to the power, actually x plus 1 to the power of 3, right? Okay, that's what you can say about p of x. Okay, interesting. And then we have to figure out what p of x actually is. Wait, why am I even thinking of, oh, the remainder theorem, of course. But you got this cubic stuff over there. Ah, right. How do you make anything out of that? You got a cubic over there, isn't it? This plus 1. Oh, God. That's something I've never seen. Right. Can't we just like, this is weird. Very weird. Okay, let's just start comparing terms, right? So, yeah, let's start comparing terms. I guess we should do that. Let's start with the constant term. So you got the constant term -1 over here. From this, you can get -1 as well. But then, yeah, okay. The constant term from m, whatever that thing is, that times -1. And, oh God, that's weird. Is this even worth doing? I don't know. And is this like a monic pointer or something? No, not knowing anything about it, right? That's all the information that we have. Okay, so just have to, go with this ax squared plus bx plus c, and then you got ax squared plus qx plus r. Okay, I hate to do this, but that's the only way out. And then you will have to compare stuff. Ah, that's awful. We don't know if it's gonna work or not. How can you even do that? Yeah, right. How can you even do that? Come on, think about it. Got -1 as a root of something, isn't it? Let's not make it 0. Oof. It's a quadratic. Okay. Why can't I think about it? So from the equality of these guys, what do we even get? What do we get from this? So what if instead of x minus 1 x plus 1 you put something else? Nah, don't do that. Okay, let's start putting x equal to 1 in there. It will just give us -1 plus 0 is equal to 1 plus n of 1 times 2 cubed. So 1 plus 8n of 2 is equal to -1. So like 8n of 2, 8n of 2 is equal to -2. So n of 2 is just -1/4. Okay, how does this help us? It doesn't. We don't know anything about what m and n do, except these are of degree 2. Yeah. God, really, we are stuck. Now, what do we do? Is there no other way? Do we actually have to compare these things? No, I don't want to be doing that. Okay, these are just constants. We start off with comparing constants. Sure. We know that constants must be the, yeah, so like whatever constant of m is there, you got -1 plus, yeah, you can actually make connections between this. Between them. I get it. Get it. It's just hard to understand what we should do. What's the fastest way out? It's a quadratic polynomial. Oh God. And then cubing and doing this. Okay, so like this is true for all real values. So start putting numbers in there and then you'll get something out. Start guessing when it's actually equal to 0. Maybe like that. No, that just, oh, and by the way, it's not n of 2, it's n of 1. So n of 1 is 1/4. How does that help us? N of x minus 1/4, that has a 0, 1. So n of x can be written as 8 times x minus 1 times x minus, I don't know, something, and that times 1/4 basically, right? Okay. That's actually painful. How is this even going to help us? Uh, yeah. Well, the a stuff is supposed to be the same for both of these. You should just write this as ax plus b instead, because yeah. So ax plus b, and then of course plus 1/4. Okay, negative 1/4 actually, negative 1/4, right? And then when you put that in there, what we get? So just get p of x is like 1 plus okay, all of this stuff times that. So 1 minus 1/4 of x plus 1 cubed, and then you got this stuff. So right, ax plus b, and that times x minus 1 and x plus 1 cubed, and that's equal to this thing. Okay, nice. And then you can think about what m is and what it's doing, right? So you can do the same kind of analysis for m as well, and just now it's going to be negative 1, so you got x plus 1, stuff like that. Yeah, it's not that bad, I guess. X plus 1 cubed, you already got x minus 1 over there. It's getting complicated bit by bit. It's getting very complicated. Okay, let's do the thing. So just put x equal to negative 1. We just get like negative 1 plus m of negative 1 times negative 2 cubed. That's going to be negative 8 m of negative 1. That's equal to 1 plus 0. So 8 m of negative 1 is equal to negative 2. So m of negative 1 is also negative 1/4. So it's going to be just negative 1, negative 1/4 of x. Well, oh wait, it should be x minus 1 over here, not x plus. No, okay, that's from this guy, so it's actually correct. And now it's going to be x minus 1 cubed because of the same stuff. And yeah, plus ax plus something, let's just say c. And then you got x minus 1 cubed, but that times of x plus 1, right? Yeah, that's the way this should be. So these have the same. Of course, you got the same a over here and this the same stuff, of course. Like, what is the constant that we get from here? Oh, it's not cube, it's squared, sorry. The constant that we get from this is negative 1, and from here we just get positive 1. And then the constants must match up, and okay, from here just get 1, from here you get negative 1. Oh god. So you got 1 minus 1/4, okay, plus actually minus b, right? So just to get the constants, put x equal to 0. That's gonna do the thing for us. So 1 minus 1/4 plus b times negative 1, right? That's equal to negative 1. Put it as 0, so just get plus 1/4. Put that as 0. So minus 1 squared is 1 times 1 is 1. And that's 1, so you got c over there. So plus c. These have the same. Okay. So b plus c. What? No, I don't want to do that. There's no way I can do that thing. Right. I get it. We can figure out some relations, but that's where we are stuck. Now, how do we even proceed? Yeah, how do we proceed? These two are equal, but that's it. Now what? Leading terms, we made those equal, and you can also figure out something about b and c. Cool. You can do all that, but after a point, you are stuck. How do you get ahead of this thing? So just by changing the constant, this completely changes, right? Okay. The polynomial pf of degree 5. I guess guessing would be a better thing to do, right? Yeah. Just, it's just changing the constants a bit. Interesting. That's the x minus 1 cubed. What's the big difference between those? Yeah, now I don't know what to do about this. It's not helping. Must be some way to get the thing. Find the polynomial. There's no easy way. Do you really have to compare everything? This is the thing that we got. So that's one equation. You got this stuff going on. Okay, these two are supposed to be the same, right? Now what? How do we proceed? We probably do this thing. 2 plus 1/4 of x minus 1 cubed minus x minus, so x plus 1 cubed, right? And then plus all of this stuff, right? So you got ax common, and also like take x minus 1 and x plus 1 common. So it's gonna be just x plus 1 squared minus x minus 1 squared. Actually, it's not supposed to be squared. It's wait, that's cube. Oh, what happened? Oh yeah, that's supposed to be cube. This is also supposed to be cube actually. Then we messed up. Didn't we messed up? Oh yeah, we did. We really did mess up. It's supposed to be negative c over there. Almost messed up. Well, whatever. Okay. X minus 1, that's cube over here. Wait, no, it's squared, of course. Okay. And x minus 1 squared. Okay, and then you got some other stuff. So you got b and c involved in there. What? Okay, so something related to b, b times, okay, and that's equal to 0. And now what? How does this even help us? It doesn't. That's the problem. Hey, actually you can figure out what b minus c is supposed to be because of this thing. So it's just 2 times of 1 minus 1/4, which is 2 minus 1 upon 2. So you got 2 minus 1 upon 2. Once again, you got like, okay, these guys, x minus 1 and x plus 1 common, right? Okay, that goes over here and everything. And then the same stuff over here as well. That should be doing it. Okay, so you got, the same stuff. So instead of doing this, you just say 2 minus 1 upon 2 in here, right? So this has 2 minus 1 upon 2. And now this is identically 0 for all values of x, right? Yeah. Wow. Now what? Stuck once again, huh? It just won't go away. Wow. I mean, you could figure out something by putting x equal to 0. Yeah. Wait, didn't we actually already put 0 there? Yeah, you can't figure that out because you got ax over here. You can't also put 1 or negative 1. Just put something else. And oh, in that way you can actually get the polynomial, but that is really not elegant. It's just brute. Okay, you can put 2 in there. I would like to see a better method to do this thing. Well, whatever. So that's it. I'm just giving up on this question. I know it can be done. I'm just 2 steps away from it, but yeah, I don't like the way I did it. So this is interesting. Okay. Yeah. Okay, polynomial equations. Whatever. Rational root theorem. Called like integer root theorem. Every rational root of this thing, okay, is an integer. What? This thing is an integer where I equal to 0 is an integer. And each of these roots is a divisor of a0. That is weird. Every rational root of this thing is an integer. So it's a monic polynomial and the coefficients are rational, then every rational root is an integer basically. I wonder why. So if it's of the form p upon q, then you got like p power and all that stuff. So the first n things, okay, n minus 1 things. Wait, no, these are n things, and the total number of terms is n plus 1. So first n minus 1 terms have so those are just multiples of p, and after cross multiplying, you got the last n terms. Those are multiples of q, and this thing it's got p power n over there and no factor of q over there, which means it's not a multiple of q because p and q are already co-prime. That means it cannot be a rational number because you just have p power n plus q times some stuff that's equal to 0, right? After cross multiplication, that's what you're gonna get. So it's not possible for the root to be, just a rational number and not an integer. It has to be both, because otherwise you get something like this. And if q is not 1, yeah, uh, the GCD of these two things is not, yeah, it's just 1. And like this is all these are just multiples of q, and that plus something that's not a multiple of q. How can that be 0, right? Okay, that makes sense. Okay, cool. So next, what you have, since all the roots are, yeah, whatever. I applying the remainder theorem. This what? What was the question? Find the rational roots of this thing. Yeah, okay. So okay, it's of the form p and q, and then you could score like p, q, and all that stuff. Cool. So 2p cube minus 3p square q, and you get the thing, something like that, right? Yeah, you have no factors of q in the first term. So, and we also like p is co-prime to q. So 2 that must share a factor with q. That's like it. Yeah, that's actually a multiple of q. That's the only way this can happen. That makes sense, right? Because all of these are just multiples of q. Then this must also be a multiple of q. If it's not, then yeah, how can you do that? Because p has no factor of q at all. So it just being a factor is not enough, right? So q is, yeah, okay. And since q divides 2, q must be 1 or 2. Okay, now it's starting to make sense how it can be useful. And similarly, you can do the same thing for that. Like you got 6 over here, all of these are just multiples of p. 6 must be a multiple of p as well. So p should divide 6. So you got these values for p. All right. And then by applying the remainder theorem, f of 1 upon 2. Okay, just, guess check basically. Yeah. Okay, that's cool. Corresponding to q. Okay, whatever. Interesting. Beta's relations. Yeah, we already know those things. Unless there's something special about it. No, there's nothing special about it. It's just the usual stuff, right? Okay, well, whatever. Okay, let's just start doing questions. Where are the questions? These are just examples. We don't want them. Okay, so find the rational roots of x power 4 minus 4x cubed plus 6x squared. Once again, using rational root theorem, it can only be plus 1 or minus 1, right? Yeah. So if it's p upon q in the whole thing and whatever. Q is, yeah, I just got plus minus 1 as the values, and then p can be plus minus 1. So either get 1 or negative 1. Yeah. Wait, okay, this is actually an example that's so easy because it's just x minus 1 power 4, right? 1, 4, 6, 4. That's how the thing is. Yeah, that was easy. It's just x minus 1 q, x minus 1 power 4. Yeah, that's what it is. So there's only one root, x equal to 1, or one repeated root. So 1 is the solution. Makes sense, isn't it? Right, the first one is very easy actually. Second, solve the equation. Okay, if sum of two of its root is equal to sum of the other two roots, so what do I do about it? Yeah, they gave nothing to us. Whatever. So you got x power 4 plus 10x cubed plus. Once again, why does it look like it's from? Interesting. 10x cube. It's like 4 degree or something. 5x, 35x squared. All multiples of 5 over there. Interesting. And then you got 25. So 24, huh? Okay. But whatever, just apply the rational root theorem and start checking stuff. So we know 2 could be a factor, minus 2 could be a factor, minus 2 could be a root. Sorry, root is what I should say. Okay. Probably not the best way to be doing it. You can probably take that 10 out. You got x. Yeah, I was just thinking about dividing by x square. Not a good idea. Don't do that. So you are saying sum of 2 of its roots is equal to sum of the other 2 roots. So okay, alpha plus beta equal to gamma plus delta, but alpha plus beta plus gamma plus delta, this is equal to negative 10. So you know, alpha plus beta, that's supposed to be negative 5, and gamma plus delta is supposed to be negative 5 as well. So it's like, is this thing x square minus 5x plus something a, and then you got x square minus 5x. Wait, okay, gamma plus. Yeah, that's negative 5. It should be plus actually. So this thing is x minus alpha times x minus beta, and this thing is x minus gamma times x minus delta, right? So plus b, of course, and now I just gotta expand and get the thing done. Yeah, that made it so much easier. Perfect. So this is like x squared plus 5x squared, which is x squared and x plus 5 squared x plus 5 squared. So 10x plus 25. And then you know a plus b times x squared plus 5x, right? And plus ab. So that's x power 4, okay, plus 10x cubed plus 25x squared. Then you got just x squared, that's where it starts. Okay, a plus bx squared. And then 5 times of a plus b times x, and then plus ab, right? Okay, that explains this 10 stuff. And also 25 plus, right, okay, that's equal to 50. So a plus b is equal to 25. Hey, that's just a quadratic, we can easily deal with that. And this linear term, where did that go? That's 50, so a plus b is equal to, oh, that's weird. Wait, is that correct? So 2 of its roots equal to sum of the other 2 roots. That's how I did this thing. Sure. And the linear term doesn't match. Why? Why is this not matching? Yeah. Oh, it's not. Sorry. You got x squared term. That's 35. So it's supposed to be 10. Makes sense actually. Right. So a plus b is equal to 10. This gives us that, and this actually also gives us that. So the linear term also, yeah. Okay, and then you got a times b, that's equal to, this is a times b, that's equal to 24, right? So just guess these two, because, okay, 4 and 6, of course. So a could be 4, b could be 6, or the inverse, right? That's going to be the two values for a, 4 and 6. So the only two values, because quadratic. Makes sense, right? Of course. So the thing is like x squared plus 5x plus 4 and x squared plus 5x plus 6. That is the thing. And then of course you can just expand. Yeah, okay. So you can factorize this easily. It's going to be x plus 4 times x plus 1. That times x plus 2 plus x plus, sorry, times x plus 3. And okay, that makes this thing. So what's the equation's solution? It's x belonging to this set, negative 1, negative 2, negative 3, and negative 4. Okay, next. Third, find the rational roots of this guy. Okay, so, you know, p, it divides 4. Wait, okay, no, it's slightly more complicated because these have a GCD, unfortunately. So you got like 6p power 4 plus, okay, all that stuff. This is not having any p, right? Yeah, this thing doesn't have any p, it just has q power 4 with it. So all of this is just a multiple of p, and that is, right, just 4q power 4. So p has to divide 4q power 4, right? But of course, oh yeah, actually this is the same as what we did that time. Sure, sure. That it still holds. P actually divides 4. or -4 or whatever, doesn't really matter. And in the same way, Q actually divides 6, but these are co-prime. Okay, P divides 4, that just means P, the magnet of P actually. That can be 2 or 4, right? Or 1. Okay. 1, 2, or 4. These are the possibilities. And then Q divides 6, that just means it can be 1, 2, or 3. Okay, let's think about all the possible pairs for mod P and mod Q. You got 1, 1 as the pair. Could work. Okay. You got 1, 2 as a pair. That makes sense. You got 1, 3 as a pair. Okay, but then once you have 2, you cannot have this thing. So it's 2, 1 is a pair, and then 2, 3 is a pair. And then similarly for 4, it's got 4, 1 is a pair, and 4, 3 is a pair. Okay, so if we just show that Q cannot be 2, you're actually done. No big deal, huh? Yeah, right. If Q is 2, what do you got? You got like 6 P power 4 plus some stuff related to Q over there. Oh yeah, don't think about it. Just got like, okay, so it's got P cube and then Q over there. And okay, it's not so obvious, unfortunately. Yeah, that didn't go like that. What about Q equal to 3? So if Q is equal to 3, then wow. Oh, that doesn't work out. If P equal to 1, then you got 6 over there and then all that stuff. Oh god, this is really weird. Do I really have to guess check? Is there no other way? I don't like how it feels. Just try something out. So let's try out the first pair. Is x equal to 1 or -1 a thing, right? So put 1 in there. What do you get? You just get 6 plus 3. Oh god. So 6 plus 1 minus 3 minus 9 minus 4. You got 7 minus 3, just 4 minus 4, 0. Doesn't work out. Put -1 in there. So you got, 6 minus 1 minus 3 plus 9 minus 4. Cool. So that's gonna be negative. Okay, that's actually 3. So 3 minus 1 is, wow, that doesn't work out at all. So the first pair doesn't work. Okay, let's try out the second pair. 1, 2. Wow, that's not gonna help, huh? Okay, but you have to try it out. So okay, let's actually just figure out these first. So put 2 in there and let's see what we get. But you're gonna have 4th degrees. That's not nice. Any other way of figuring it out? Special stuff that I can apply. Multiple of 3, multiple of 3, multiple of 3. Just got x cubed minus 4. That must be a multiple of 3, right? Okay, after the factorization stuff. What will you get? Just get like the pq. Okay, that's p power 4, right? So you're going to get p cube q minus 4 cube. So p cube q minus 4 cube. 3 actually divides this thing because only then it will actually do the thing. Yeah, okay, awesome. Right. So when can this happen? I mean, it's like, okay, 3 divides q times of p cube minus 4q square, right? Okay. So either p divides q or it divides this. Yeah, wait. It's co-prime with that. I mean, okay, q is actually co-prime with this whole thing because this has factors of q, all the factors, but that's a co-prime number added to that thing. What does that mean? It either divides this or that. Yeah. So if p divides q, then q has to be 3, or mod q has to be 3, right? So yeah, you will just have to check these terms in that case. Okay. Interesting. And then you can do the same kind of stuff for the even terms. So you got this whole stuff. It doesn't have any even terms in there. So x cubed minus 3x squared minus 9x, that must be a multiple of 2. That must be even, basically. Okay, after the whole factorization stuff, what you actually get is p cube q minus 3p squared. What am I doing? Maybe maybe I'm just analyzing the whole thing. Maybe I'm not. Who knows? So 2 divides this thing, right? Okay. So basically like 2 divides, we take out some stuff. PQ is common. We got P square minus, okay, P square minus 3PQ minus 9Q square, whatever, right? This thing is, right, not a multiple of P or Q. Okay. So it either divides P or it divides Q or it divides this whole stuff. Right. Okay, this is weird. Yeah. So like if it divides this whole stuff, it also divides this thing. That's odd and that's odd. So you can make this thing happen. Interesting. One of these has to be odd, right? P and Q can't be both even. So that just means like this whole thing is just an odd number. But then this thing is an even number, right? Because one of them has to be odd, one of them has to be even. Look at P, man. Look at P. If, okay, maybe that's not the best way to do so. Okay, if both are odd, what happens? This is getting weird. If both are odd, then P square plus Q square is an even number, and this thing is an odd number, which doesn't make any sense. If both are even, well, that's nice, but then they have a GCD, doesn't make any sense. If P is odd, Q is even, right? Or the inverse. It's gonna get like, that's odd number and that's an even number, so it still doesn't work out, which means that actually it cannot ever divide this thing. So 2 cannot divide this thing, it has to divide one of these guys. So you can divide P, that's probably what's going to happen, or it could just divide Q. If it divides Q, then you've got this stuff happening, Q equal to 2, which is this thing. That's the only possibility. Okay. And P equal to 1, that's here. And wait, if it divides Q, then, oh, then P has to be 1, right? Co-prime, of course. That's not leading us to anything, Yeah, not helping. God, what do we do now? What do we do? Well, 3 has to divide this stuff, huh? P cube minus 4Q square. P is definitely not something that's a multiple of 3. Q could be, but if Q is, then that's problematic. You cannot have Q being a multiple of 3. Wait, actually no, if Q is a multiple of 3, then this is a multiple of 3 as well. So in all situations, actually does work out. Wow. Nope, not even giving us a hint about what we should be doing in this kind of situation. Right? Okay, we at least got some good guesses at what the roots could be. It could be like plus minus 1, plus minus 2, plus minus 4, plus minus 1 upon 2, plus minus 2 upon 3. But there are 7 such cases. Then how are we supposed to do that in a limited amount of time? Yeah, what I'm thinking of is that these are not going to help us. Yeah, if you actually have to figure out roots, do it in a better way. Don't rely on these, I guess. So any other better way we know of to do this thing? No, actually. Yeah, that's the problem. We don't know if there's a better way. 6x power 4 plus x cubed minus 3x minus 9x minus 4. Well, x cubed minus 3x squared, maybe you can use that to complete the cube or something. Okay. X power 4. That's 4 over there. Think about it. Take its derivative, you could, but 12x power 3 plus 3x squared minus 6x minus 9. So cubic, not helping. Definitely not helping. But it did get all multiples of 3, so if I did take a derivative, it's like 12x cubed minus 3x squared minus 6x minus 9. You could factor out a 3 from that. It's got 4x cubed minus x squared minus 2x minus 3 or something like that. Okay. Doesn't really help us. Is this always increasing or something? Well, we take that guy's derivative. 12x squared minus 2x minus 2. That reduce that. Got 6x squared minus x minus 1. It's not. This thing is changing its sign. So no, don't worry. That doesn't work at all. Any other trick that we can do using complex numbers or something? I don't see that happening anytime soon. Do we really have to guess check these 7 cases? No other way around this? Wow, that's not good. Okay, can it be an integer, right? So I mean, just get rid of these first 3 cases maybe. Can it be an integer? Oh, that's once again going to be PONQ format and everything. Not worth doing it. Not worth doing. Or if it's supposed to be multiple of 4 or something, right? You take the x out, it's got this guy. 6x cubed plus, no, not, don't spend time on that. There's no way actually that we can do this on time because you got 7 cases. How can I do this? Just start checking all the integer roots. No. Okay, check 2. Who knows? I don't think it's going to help us, but if it was meant to be solved, we have to solve it, right? Okay, let's try it out. Let's try, yeah, let's try it out. Try out 2. This is gonna increase much faster than these guys. Well, I'm thinking -2 might be better because, you know, you got -x cube supporting the stuff. Whatever, just start off with 2. So you got 12 times 2 power 4, that's gonna be 24. 24, and then you got plus x cube, which is 8, and minus 12, then minus 18, and minus 4, right? This will be 4, 28 minus 18 is 10. That's -2. We are getting closer. So, right, let's keep going. What about 4? So if you put 4 in there, from the first 3 terms, you can take x squared. So you can take 16 out. You're gonna get 6 times what? 16, which is 96. Then plus x, so plus 4. Then minus 3, I guess. Yeah, that's just too big. Yeah, just too big, huh? Okay, minus 9 times 4. And then minus 4. Reduce that. So it's gonna be this guy. It's -1 over here. Nope, won't help. Okay, so these are not helping. 2, 2, 4, nothing. Nothing's happening. You could check -2. I doubt that's going to help us. We're going to have negative over here and positive in this area. Yeah, you can see that this is already much bigger. So, you know, it's going to be 10 and then, like, what is this? It's 20, 30, 30 minus 12 doesn't work out. No hope for us. How do you solve questions like these? Without, of course, a brute force method. Is there any way of solving this correctly, right? Okay, I guess we should stop for now. Yeah, right. We'll see you guys in the next video.